Today we're going to start with Chapter 11, Graphical Solutions. So we're going to learn how to properly plot both experimental data series, data that you collect, and also theoretical data series. So theoretical represents the equations where we calculate and then graph the solutions for that. So we need to start with our terminology for our graphical solutions. And so here we have our axes. And our axes we've normally at this point referred to as our X and Y axis when graphing. But in engineering, we actually use the terms abscissa and ordinate. And so your abscissa is that x-axis, which is your independent variable or controlled parameter for your data series. So this is usually I'm measuring things at a time or a distance or a height. And then as I measure at those increments, I'm getting what is on my ordinate, which is my y-axis or dependent variable and measured parameter. And so remember that x comes before y, so our horizontal comes before our vertical axis, or our abscissa comes before our ordinate. And so for proper plots, when we start plotting, there are some key features that need to be considered when you put your plots together. So first we need to label our axes. And so when we label our axes, we have three parts to that label. We have what that variable is. So in this case, time. We have what the symbol is in parentheses. So for time, it would be a lowercase t. And then what units we measured these or collected our data in or had our interval in. So our units here for time found in our square bracket is our seconds. And so we could also say we have density. Maybe density was our outputted or our ordinate variable. We used our Greek symbol rho in parentheses to represent density, and then our units for density are grams per centimeter cubed or grams per cc in our square brackets. Also, we want to make sure that we have a descriptive title or caption. And normally, you are going to graph something in Excel, but then you're going to output your graph into a Word document or a report. So in that case, we do not need a title. More likely, you're going to use a figure caption to explain exactly what your plot is about, what your data represents, what trend you're seeing in your data, things like that. And so you're going to describe exactly what your problem is or what data you collected, how it's represented in your graph. So things like D versus T or distance versus time, relationship between or as a function of are things that we want to be more descriptive about when we are using our figure captions. Also, on the axis, we have our numbers. And so these are our scaled increments. And so we want these to be easy to read and interpret between. So we usually pick increments of 1, 2, 2.5, or 5, so that we can scale these up by a power of 10. So if we have 2.5, say we're scaling by a power of 100, you're talking about 250, 500, 750, 1,000. And so we want to keep those increments easy to work between. So we don't want to use unusual increments such as 3, 7, 15, or 6.5, because those get hard to interpret between our different increments. So looking at different graphs, let's talk about grid lines. So grid lines are important for being able to determine or interpret between. So we usually add our major grid lines. So we have both horizontal and vertical grid lines. So graph A here has no grid lines at all. We do have our values and our axis labels, but if we're saying we're trying to read at 27 seconds, it's somewhere in here. It gets a little hard to pinpoint. So on graph B, we're going to say that we've got between 20 and 30 seconds here. If we're saying 27, we're in this area here on graph B. And so it's a little bit easier. We at least have a line here to carry forward that we might say is 27 seconds. So this comes out to be a voltage of 2 volts. Or we can say graph C where we've had our vertical grid lines, 20, so we can go off of 20 and 30. Well, so maybe that isn't quite 2 volts. So when we start adding both our major and minor grid lines, then we can get a more accurate measurement of where 27 may be. So D is our best option, adding both horizontal and vertical grid lines. So all of your plots need at least the major horizontal and vertical grid lines. Sometimes if you have a lot of points in between those, you're going to want to work with your minor grid lines as well. So what are our two different data series that we normally graph on a scatter plot? Well, we start with our experimental data, or this measured data that you collect during an experiment. And so this is normally shown as discrete symbols or markers, points on a graph. So using different symbol shapes or marker shapes and a color for each experimental data set is necessary, because in most publications, you are not going to have your graph printed in color. And so if we're talking about a black and white image, you want your data points to show up nice and crisp on your graph, but you also need to differentiate by different marker styles and color in order to be able to read that or differentiate between your data series. With our theoretical data, this is calculated data that comes from an equation, and we display this as lines on our plots. And so again, if you're using multiple data series for our theoretical data sets, you need to have a different line style and color in case we were to turn our graphs into black and white images. And so in doing so, if you distinguish your curves and symbols for all of your data sets, so in the case here, we've got a purple square, a red triangle with a white center, a blue circle. All of these could be used on a single graph to differentiate between data series. And you want to use dark color so that it stands out on your graph. And so color alone is not sufficient to differentiate. When we get to theoretical, we have different line styles and different colors. So we've got a black solid line, a short dashed green line, and then a dotted blue line here as representation. And you want to make sure that you stay away from yellows or light colors in your graphs because those get really hard to see. And you want to make sure that your data shows up. And then lastly, if we have two or more data series that are present on a plot, that means that you need to include a legend. So your legend is not used for a single data set, only for two or more data sets. And then when you add your legend, you want to make sure that you have meaningful series names. So Excel will automatically add series 1, series 2, series 3, but that doesn't tell us anything or what that series represents. So let's look at an experimental plot. So here we've got an experimental plot with multiple series. So we've got our abscissa, which has height, our symbol H. We're measuring this in meters. Our ordinate is representing power, P, in horsepower. Then we have two separate data series. So we have mass of 100 kilograms represented by blue diamonds and a mass of 250 kilograms that is represented as red squares. So our points are both different colors and different styles on our plot. We've got both major and minor grid lines. And we've got great increments that do not contain additional decimals that are not necessary. So here, instead of saying 0.2500, we're just reduce this down to 2 decimal places, 0.25, as we don't want any further zeros represented to take up space on our plots. And then you're going to notice here we've got our figure caption at the very bottom, so figure 11-5, example of a correctly drawn plot showing experimental data. And then lastly, looking at a theoretical single data series, again, we've got our axis labels with our 3 parts to each label. We've got our numbers or our increments here on each axis that are represented nicely. We've got our major and minor grid lines in both horizontal and vertical directions. Our single data series here is represented by a red short dashed line. And we do not need a legend in this because we only have a single data series. So we're going to stop this video here and we are going to move on to our Excel demo file.